It's amazing that any of it gets done, and it's amazing that it's been getting done since the beginning of time when we needed to build shelters in the first place.
Welcome back to Curiosity Class, the podcast where we break down complex topics into easy to understand ideas and bite-sized pieces. My name is Jeff Album, and I've been a curious person my entire life. Inspired by Albert Einstein's quote, "If you can't explain something simply, you don't understand it well enough," we aim to make learning accessible and engaging. On this show, we're going to bring you experts from various fields, ranging from personal finance to physics, to help you understand everything from 401ks to how airplanes fly. So let's dive in and satisfy our curiosity together. What's going on, everybody? Welcome back to another episode of Curiosity Class. Today, I am very honored, very humbled to be joined by my very good friend, Hetsroni. He is a structural engineer. His background, he got his undergraduate from Cal Poly San Luis Obispo in civil engineering. He got his master's in structural engineering from Cal State Northridge. And I'm super excited to have him on here today to talk to you about structures, man. Let's do it.
Yeah, let's do it. I'm happy to be here and happy to be a part of this.
All right. So before we get going, I kind of want to know your background a little bit about, like, were you one of those guys who saw Prison Break and the guy on Prison Break was a structural engineer? So, like, I'm going to be him. What got you into it?
So it all started, my dad started a construction company back when I was a little kid. And so I've kind of always been around the construction industry and, going to his office and seeing a bunch of blueprints and building plans. And I just found that super interesting, and knew that I wanted to do something in the field of building. Um, and then in high school, I took a physics class and I was like, oh, I love physics. Like maybe I can combine the two. Um, and it took me a while to get to that because I loved physics in high school and then went to Cal Poly and started as a physics major. And it took me 3 years to realize like, oh, I don't want to be a physics teacher and I don't want to be a researcher. Like my ultimate goal is to do something in the construction and building industry while also mixing that with my passion of physics and kind of understanding how the world works in terms of equations and numbers and the laws of physics, you know?
Mm-hmm.
And so the perfect combination of those two things was structural engineering.
Fair enough. Okay, so not
Yeah,
Prison Break.
it was not Prison Break. I've never seen Prison Break.
Really?
Oh yeah, add it to the
Oh
list
man,
though.
100%. Okay, so once you got into structural engineering, was it a pretty easy path? Like once you found it, you're like, okay, cool. This is what I want to be doing. Like this is what I love to do. Was it pretty
So
obvious?
it was it it was because I think Cal Poly sets you up to like start working right out of college. Um, that being said, the path that I took coming from physics, switching in my third year, it made it a little more difficult because like I'm almost getting a physics degree at that point. It's like I think it was probably like I don't know 6 or 7 more like physics classes, and then I had a degree in physics. But I was like, mm-mm. um, so I ended up I tried. So Cal Poly has a program called architectural engineering and then civil engineering.
Okay.
Architectural engineering is for people who want to like go straight into structural engineering. They know for a fact that's what they want to do. So I was a physics major and I knew that's what I want to do. I went to them and the department head was like, "Well, you're already in your third year, which means in your fourth year you're going to be starting studio classes. That's like a 3 year minimum, and then it's already a 5 year program. You're going to be in at Cal Poly for like 8 years if you switch now." So he was like, "No, we're not doing that." Um, and then he referred me to the civil engineering department. And so the difference between the two, Archie and civil, is Archie is only structures, and then civil has geotechnical engineering, transportation engineering, water engineering, construction engineering, I think, and structural engineering. So you
Okay.
study a broad spectrum of all of the civil disciplines, and then you pick one as your concentration.
And what's
Uh,
the difference between civil and structural engineering? I'm sorry, construction and structural engineering.
so construction it's so similarly tied to construction management.
Okay.
Um, I personally think it's like the difference between doing your major in civil with a emphasis on structures and archi. They're basically the same, just through different programs, and then same thing as doing construction management or civil with an emphasis in construction engineering. That's at least my understanding. I only had one of my friends who actually did construction engineering. All the rest kind of switched into construction management because why not? Especially because Cal Poly has a great program in that too. Um, Long story short, my path was like this, but I think the idea is that you get your degree in structural engineering or civil and structures, and then you start working right after. The other thing I would say is that at Cal Poly, the architectural engineers come out with a much more in-depth understanding of how structural engineering works, just because they've been doing it for 5 years at that point, where when you do it in civil, you get a very broad of everything, and then you scratch the surface of a particular subject for like the last year or so. So you can tell, the first place I worked after college was a place where I would say 90% of the structural engineers were from Cal Poly. Um, and you could tell, like, oh, here are the people that were in civil, here are the people that were in architectural engineering, because one side has so much more knowledge coming out of school than the other, and it just takes the civil engineers like a little bit more effort and more work to get up to where the archies kind of graduate. But the idea is that both of them go straight into into working in that field.
Got it. Okay. So taking a little bit of a zoom out, when we're talking about a project, right? Like, what is the role of a structural engineer as opposed, like, can you define, like, okay, you have your architect, you have your general contractor, you have your structural, like, where does the structural engineer fit in, and like, what is the overall project team look like?
That's a great question, and I'm gonna start the answer by saying every time someone asks me, "Oh, what do you do for work?" and I say structural engineering, they say, "Oh, so you're an architect?" And like the answer to that is no, no. I said I'm a structural engineer. But our kind of role in that general team, if you like, let's say I'm doing a building. The building has a left brain and a right brain. The left brain, I think, is the math science side, and the right is the whatever way is the creative side. That's the architects. They have like such a good understanding of like how a space works, where to put the bathroom, how like traffic flows through a building and how big a room needs to be. Like, I have nothing to do with that. My role is to take their plans and their like, artistic, creative kind of creation, and then work it into the world of physics and engineering, and kind of massage it into, this. You need specific material and specific structural requirements to make this building stand laterally, when earthquakes or wind move it left and right, or in gravity when things are trying to push it down and you're trying to hold it up right. So the architect is the designer of the plans and designer of, how the house flows, or the creative side. They're the ones who spend time like looking at mood boards and inspiration of, like, how does this trim look with this roof tiling, right? And then they hand off the plans to me and say, hey, we've chosen all of our tiling, we've chosen all of our wall thicknesses and our finish thicknesses and all of the weights of the flooring, and everything is fully decided. We need you to engineer it now. And so that's where my job takes off. And it takes us some time to get through the actual design and engineering of the building itself. And there is a lot of back and forth between us and the architects, like, hey, you didn't give us enough like wall wall thickness or wall linear length in this certain area. So like we can physically do this. It's going to be way more expensive than I think you want it to be. Can you please just give us one wall or one column here? Or can we move some things around to make this to make it fit your budget and we can engineer this successfully for you. Um, there's a famous line which is anyone can design a bridge. It takes a civil engineer to design it just as cheap as possible while making it just barely not fail. like, like we can design any wall to 99% of its like structural capacity and be like, hey, this is what you need to do for your wall, and it's going to be as cheap as possible. Where anyone could be like, oh yeah, let's just make the whole building out of steel, and then okay, well now
Mm,
you have a super expensive building that will stand through an apocalypse. Um, but yeah, so that's kind of the role of the structural engineer. And then we hand our plans back to the architect. The architect sends it into the city. The city has comments about any kind of issues that would have come up, um, and then hand the plans back to us. We give it to the contractors. Contractors build it, and that's kind of the process and where we fit in. And we're structural engineering discipline is in the same realm as the plumbing and the mechanical and lighting. And so like the architect finishes their plans and hands it to all of us at the same time. And it's like, all right, everyone go and get back to us with where all of your stuff is going so we can turn it in.
got it. Okay.
Yeah.
And so, like, something I've always wondered is like, why are those all separate companies? Like, why isn't there companies that does architecture, structural engineering, mechanical engineering, electrical engineering, plumbing design, like all that under one house?
I think there are a couple of companies that do it, but I think that um, I think there's a couple of reasons. One, I think a lot of it is liability, where you're putting so much under one umbrella that you are fully responsible for anything that goes wrong. As opposed to like a conversation back and forth of like, hey, we messed up on this thing. Can you switch some things around? Oh, sure, yeah, we can move this around as long as the plumber can move their plumbing lines in or out of an area. As opposed to like if it's one company, everyone is kind of responsible for everyone else. That's why I think, and I think me and you have had conversations in the past where we're yelling on a phone of like, it would be so much easier if I didn't have to send an email if I could just walk over to someone's desk and be like, hey, move your wall. Like, it would just be
Right.
easier. Yeah, but it's just so many disciplines under one roof. I mean, yeah, that's kind of my thinking.
But yeah, I feel like that would be so much more effective because you would be able to finish the project so much quicker in theory.
In theory, yes, you would. Yeah.
Huh. Okay. Interesting. Okay. Now I want to move to like buildings themselves. So I've been fascinated with buildings basically my entire life. I was one of those people who saw Prison Break and wanted to be a structural engineer. Um, and I actually don't remember why I didn't. I think it was at the like when I was applying to college, Archie was super impacted, and I was like, I don't know about that. But okay, yeah. So I want to start at like, no pun intended, from the ground up. So
Yes.
if you're looking at a piece of dirt, you have like raw land, you have nothing there,
Yep.
and I'm like, hey, I want to build a building here. What's the first thing that needs to happen? And then I want to get to like what the foundation actually means. Like, what is that?
Okay, so you're looking at a piece of land. The first step, if you want to build a building on it, is to get a geotechnical engineer out there onto your land and take samples of the soil. Usually, on most typical residential projects, it's I think it's 5 samples from around the site. So they'll take that sample and then go back to their lab and test it, and it takes a couple weeks, but they get back to you with a report saying, "Hey, um, here's what kind of building you can build. You can build on it. Here are based on your location and your proximity to like a fault line. here's what you can expect the ground to shake at different intervals and different forces that it will apply to your building. Um, they give you all of like the pressure, like so if you have to build, if you have to like, dig down into it, they give you all the pressures on like the retaining walls of like lateral pressures and any water pressure and what that needs to be designed for. They basically just give you a full rundown of like, hey, this is how you need to start your project, and here are all your basic design values. Once you get a report from the soils engineer, you can start your design. And I know that you wanted to start at the foundations, but to get to the foundations, you have to start up above. We start at the roof level and then make our way down to the foundation. It's the opposite of how it's built. So we start with the roof.
And when you say we start, that's like from a structural engineering perspective.
Yes, from how we're going to design this building to withstand certain forces, we have to start with the roof. And that's not to mention that there is a process before design starting at the top. Very, very briefly, from the soils engineer, when you get this report, it gives you certain values of how close you are to the fault line, right? And from there, it's called the equivalent lateral force procedure, which we call ELFP for short. And what it basically does is gives you it's a statistical analysis of how likely an earthquake is to happen, and gives us a design value to base our building off of, based on the geotechnical engineer's report. So once you go through that procedure and put in all of the geotechnical engineer's report and put in some values from your specific site and from your specific project, you can get a factor called the CS factor, and that's what you apply to your building to get forces. So that's very general overview.
What does CS stand for?
I don't remember off the top of my head.
Okay, but it's something to do with earthquakes.
Coefficient of something. Yeah. Coefficient of something, I think.
Okay.
But yeah, so you get this factor, and it's usually in the industry I'm in, it's usually in the realm of like 0.2 to 0.4, let's say. And
we should also say the majority of your projects are in California, correct?
Yes. So I will also say this: the majority of my projects are in California, and the majority of my projects are single-family homes on the higher end, because I work in LA. So these houses are typically heavier than the normal house, a little bit more higher end finishes, and very much more custom and specifically detailed and built, as opposed to like your run of the mill 2-story house on a residential neighborhood block. We also have to deal much more with landslides and crazy slopes, because we're building in the hills of like Beverly Hills and the hills of Hollywood. And so we at the company that I work for, that we deal with a lot, at least my team deals with a lot more kind of structurally complicated structures, rather than some kind of a more boutique structural engineering place would just be, hey, I need an ADU. Great. It's a flat site. It's a pretty easy design. It takes, a week or two.
Got it. Okay.
And the other caveat I want to say is, so I've been doing this for 5 years now, coming up on 6 years, which in our industry, I think is still pretty relatively new. I think at this point, like I'm really good at what I do, but there is definitely like a next level of complexity, and a next level of like understanding how the buildings work and how all of these factors get put together, and another level of complexity when it comes to engineering judgment and making decisions based on experience, where I'm still gaining experience every day. and I
Mm-hmm.
can use some of it day to day. But a lot of it I have to run by my manager who's been in this industry for 15 years. Um, and so I'm still, working towards getting um, more proficient in my industry. So that's what a caveat to the entire conversation is I'm still in the learning process. I think as we all are. But yeah. Um,
Fair
but
enough.
back to the just general discussion. Um, and an attempt not to bore everyone about
Okay, we're at
complicated and
well, no.
boring.
So go back to roofs.
Yes, back to roofs. Um, so you start at the roof, and what you do is you take all the architectural finishes and designs and roof, slopes and pitches and ridges and beam whatever, um, and you come up with a weight of how much is all of this roof going to weigh, like in total. So if you want
Okay.
Spanish tile, that's heavier than asphalt tile. If you want asphalt, if you want um, standing seam metal, that's one of the lightest you can do. Um,
So
and so you,
wait, quick question. So,
yes.
okay, what's like a tip? Okay, the roof of a single family home that's in a residential neighborhood that's been built in a subdivision. Just for
Mhm.
reference, like how much does one of those roofs typically weigh, or give us a range?
The general range, I want to say, and we do things in terms of per square foot. So
Okay.
it's anywhere in between, I'd say anywhere from like 14 pounds per square foot to like 30 pounds per square foot. And that's
Okay.
again, that's dependent on what kind, like, do you want Spanish tile? Spanish tile itself
Right.
adds probably 12 pounds per square foot. Um,
Oh, wow.
Yeah. So and that plays a role into everything that goes below it, you
And
know.
so, do you like what if someone, if they want solar panels? I'm assuming that's
An
more weight that
additional.
you have to.
Yep. Yes.
Got
So
it.
in
Okay.
California, at least it's for California. It might be for other states too, but we are code required to account for future solar on every new build that we do, which is an additional 4 pounds per
Mm,
square foot that we have to add to every roof, even if the architect says there's no solar, there's never going to be solar. You still need to include the 4 pounds per square foot.
got it. Got it. Got it.
Yeah,
Okay.
that might
Cool.
be a Los Angeles mandate. Maybe not a California one, but it is. It
Okay.
is. Yeah.
So you start with the roof, you get a general
Mhm.
idea of okay, what's this thing gonna weigh per square foot, and then
Yes.
and then what?
So that's where you start on that roof. You get that number, and then you do the same thing for the floor below it. So the second floor, if you have a second floor, and
Okay.
you get the weight of the bathroom tiles and the floor and the hardwood flooring. You include the weight of the walls. So any wall finishes, stucco, plaster. That includes ceiling weights, by the way. So all that like gypcrete board, like panels that they hang from the ceiling. That includes all of that. And the idea that why we're getting these weights is if you know picture a rod that is the height of your building,
Mm-hmm.
um, where the base is fixed, and then at the second floor, like when you go up the stairs, that second floor is
Mm-hmm.
we're going to pretend like that's one ball of mass. We're going back to physics class here. That's one
Okay.
ball. That's one ball of mass, and then you go up to the roof, and that's another ball of mass. We're trying to
Uh-huh.
figure out the weight of these balls of mass, so that when you shake the base, the ground, we can
Uh-huh.
determine how far these balls of mass are moving and how, with what acceleration and what their displacement is based on the forces and what the forces are based on the weights. So we're just running an analysis of a very basic physics analysis of like a pendulum, let's say.
Okay. And this is all I mean, this maybe sounds really stupid, but I guess I've never thought about a house or any structure in terms of its weight. Like
Yeah,
I've never had that thought, which is I mean, as I say it sounds really silly, but that makes a lot of sense. Like,
yeah,
okay, how much does this thing weigh? That will really affect what we need, to design the beams for and the structural elements like that. That's very logical.
Yep. And if you take yourself back to Physics 101, the equation to know is force equals mass times acceleration. F equals ma. I don't know if you remember that,
Mm-hmm.
but that is it burned into my brain.
Mm-hmm.
And so, in order to get the force that we need to account for um, in a building, that's the force that we are going to design to withstand, so that our building isn't, when an earthquake hits, toppling over, or the roof isn't gonna fly 10 inches one way or the other and shake you while you were sleeping. Um, and so force times mass, or force equals mass times acceleration. You know your acceleration based on the Soles report and based on your location to a fault, and a statistical analysis that you run on top of that. You need to know your
Got it. Got
mass,
it.
which
Got
we
it.
just did with all of the roof weight and the floor weights, and that's how you get your force, mass times acceleration. Um,
Wow.
yeah.
Huh.
So that's how you get your forces. And the next level beyond that is, now you have your force. How are you going to withstand that? How are you going to resist that force? Um, which is, you basically have, you have a couple options. And this is what I was talking about in the beginning, where there's lateral forces, which is how we're going to
Mm-hmm.
resist these earthquake forces.
And
So
lateral. So if people can't see, lateral is left to right, right?
yes, left to right, and
Or
we go by north, south, east, west.
okay.
So we design a building to withstand forces, uh, a hun- 100% in both directions, because the idea is, the
Both
worst
directions
case.
meaning north, south, east, west, but also up and down. Yeah.
Yes, yeah, yeah, exactly. So
Okay.
like, the building is going to shake in any direction 360 degrees around a circle, right? But we
Mm-hmm.
need to design in each direction in the worst case possible, just in case a building is situated in the way where, like, the earthquake is shaking the earth, and it happens to be in the direct cardinal direction of east west or north south.
Mm.
So, like, let's say we put down a building and an earthquake happens, and in that earthquake, it shakes in a direct 45-degree line from, so it's exactly northeast, or let's say, for example. Um, now you have, okay, you have total control, where we've designed for the worst case in the north south and the worst case in the east west. Therefore, if you have half on one side, half the other, we're good on both.
Right. Right. Right.
Does that make
Okay.
sense?
Yeah. And
Um,
so when you're designing these, so okay, how are we getting to the foundation? How does this relate to the foundation?
yeah, we're making our way down. We are making our way down. Um, so 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 we're at the roof. We got the floor, and the weights go down into the foundation. And so that's the gravity portion of the foundation, where you take those weights, and those weights need to be dissipated into the earth. Um,
Okay.
Let me think of a good analogy. Let's say the earth is a piece of paper, and you put a pin needle in that piece of paper, and we're gonna represent that pin needle as, like, a column coming down that's taking a big beam weight, or a post that's coming down and taking a big beam weight. That
Okay.
pin, when you press, the harder and harder you press, that's gonna go right through the paper.
Right.
Um, if you add like a square block underneath that pin, when you press the pin down, it presses the whole square block down, engaging more of the area of the paper, so that it
Mm-hmm.
won't it won't sink into the ground. It won't
Mm-hmm.
sink through the paper.
Mm-hmm. Yep.
That's the idea of the foundation. Is we're just trying to dissipate these loads and spread them over as large of an area as we can, while keeping it structurally efficient, while keeping it cost efficient, and thinking about the client and what the architectural needs are.
Got it. So it's literally just like, okay, how big's our building? What are the forces at play pushing
Mm-hmm.
down, right? Because we have like the roof and the walls and like the second story and the first story and all that weighs something plus gravity. So
Yep.
then we need to figure out, okay, cool. Like if people remember tell me if this is the right way to think about it, but going
Yeah.
back to like everything has an equal and opposite reaction. So
Yeah.
if you have 100,000 pounds pushing down, you need to have
Hmm.
something that can have 100,000 pounds to push up so that it doesn't move, right?
Right. Right. And your soils engineer will give you a value of how strong is the soil beneath your house.
Got it.
How
Okay.
much can that soil resist until it totally crumbles and your whole building is going to start sinking into the ground, or one side is going to sink farther than the other side. You're going to have differential settlement. You're going to get cracks in your walls and your foundations. It's going to be
Mm-hmm.
horrible.
Right.
So we need to design to a certain level of like, we need to dissipate these forces so that we're not disrupting the soil. We're just sitting on it.
And so like are all foundations concrete or not necessarily?
They are all concrete, but there are so many different systems that you can use. I think back in the day they used to be able to do CMU blocks for which is those like cinder blocks basically
Uh-huh.
for foundations, but I don't think they're allowed to do that anymore because I haven't seen it.
Okay.
I checked out like one old house and saw it, saw a foundation of a CMU blocks and thought it was pretty strange.
So I guess like what I'm still trying to wrap my head around is like, okay, going back to our raw land example, right? So you have raw land, you get your soils engineer out there, they're taking tests, they're giving you your what you can build there, they're giving you pressures and all this stuff. And then you're
Mhm.
like, okay, cool, we can build a building. Great. So now I'm assuming you get a bunch of big pieces of equipment to come in and move a bunch of earth, right? And so you're
Yeah.
basically like digging a hole. And then
Mhm.
where I've seen them, it's like, okay, you dig this hole, you like compact some of the soil, and then you're
Mhm.
pouring concrete as the foundation,
Mhm. Yes.
right? But like
Yeah.
what I'm kind of confused about is like, okay, cool. Now you have this concrete foundation. I get it that it's dissipating the force of the house, but and maybe this is a silly question, but like, why is the whole foundation stay? And does the foundation itself not move? Like, what's attaching the foundation to the earth, if that makes sense?
That does make sense. And that is also something that structural engineers need to think about
Okay.
because, um, well, the idea is you're digging out these trenches to put the foundation in.
Mm-hmm.
And by the way, the foundation is different than the slab that covers the whole pad of the building.
Oh, interesting. Okay, so I definitely did not know that. So what's the foundation versus what's the slab?
So the foundation are trenches that are dug out in specific places designated by the structural engineer.
Okay.
Um, it's usually the whole perimeter of the house is usually one what we call a continuous foundation, um, which just for reference on a residential project that you were talking about, very typical, not fancy at all. Usually 18 inches wide by 18 inches deep, sometimes 12 inches deep, depending on the soils report, but it's usually 18 by 18. And then you usually put two number four rebar at the top and bottom. That's like very basic. You kind of see that on every project.
So
Um,
you basically have this trench running the perimeter of the footprint of the house in this case.
Correct.
You dig a trench 18 by 18 and then you
Correct.
add rebar in and then do you pour concrete into that?
Yes. And then you fill
Okay.
that all the way to the top with concrete, so you have an 18-inch deep concrete footing.
Okay.
And that's
Oh,
what
that's a footing. That's what that is.
it's called the footing. Um,
Oh.
and so that goes around the perimeter, and then depending on the architectural plans and what the structural engineer decides, where this weight is going, because we can choose. Let's say the architectural plans say, okay, on the first level, I don't want any interior walls. I want a blank open space for whatever reason. So now we need to think about how we're going to move all of the gravity loads to the exterior walls using beams or steel beams or wood beams, um, or joists, spanning in certain directions to move the weight out to the perimeter. But if the project is big enough, um, and the architectural gives us wall spans in the interior, well, now we have load bearing walls, which you hear on HGTV all the time,
Yes.
where, oh, this is a load bearing wall, we need to do something about that.
We can't
Um,
move it. It's a load bearing wall. Or we can't
correct.
demo. It's a load bearing wall. Okay.
Correct.
Got it.
Yeah, so when you have interior load bearing walls, you also need to put a continuous footing underneath those because load bearing, as the name suggests. It's taking load from above, and we need to send it down into the earth, right? So like, all right, we have our
Oh.
perimeter footings. We now need to figure out which walls we're going to use as load bearing walls, so we can figure out where we're going to put those interior footings.
Got it. Got it. Got it. Got it. Okay. Okay.
And
And
then
so, and sorry, yeah, continue.
the last piece of that is, sometimes there's locations where you don't have a wall, but you have a post where that's taking a lot of load. And so under those, you won't put a continuous footing. You'll put what's called a pad footing, which is usually like a 2 foot by 2 foot square, um, 18-inch deep little footing that's just taking that load and dissipating it. It's just not in a linear fashion. It's one little pad that they pour, dig out and
Got
pour
it.
in the same way that they do continuous footings.
Got it. And so all of the footings, do those make up the foundation? Like what's the difference between footings and foundation?
Footings are foundation. Foundation is the umbrella term for anything that is helping load get dissipated into the earth. Um,
Got it. Okay.
And so different types of foundation, depending on where your building is located and how structurally intense it is to design for. Like for example, the houses that we do up in the hills, well, we don't really have a flat land where you can pour footings and comfortably sit on them, right?
Right.
You
Right.
have crazy slopes that you're trying to hang your building off of, to look spectacular. So the way we need to do those is, those are called pile foundations, where
Okay.
you pour this cylinder of concrete, usually starting at like 24 inches in diameter till they get as big as, like, I mean, they get bigger, but the biggest I usually do are like 30 or 3 feet, 36 inches in diameter. And
Okay.
you send those way down deep into the earth, to resist the loads, of your building.
So those, we can think of those as kind of the same thing as in the flat house example. You have like if you have a post or a column or something that needs to
Mm-hmm.
get like the, you call it 18 by 18. It's a, oh, what kind of footing was it? Not linear, but
Pad footing.
pad footing. So it's kind of like that, but just way deeper.
Yes, and yeah, and the idea behind those are you're using, the friction value between the soil and that concrete cylinder
Uh huh.
to resist the down force that pile is seeing. So like,
And but these are probably super deep, right? Like these are not just 18 inches in the earth. Like how deep are
no,
these
no,
going?
no. They go minimum. They start at 8 feet. The maximum that
Dang.
I've done is probably around 100 feet deep.
Oh.
Yeah, yeah, yeah. So they get sent down into the earth, like way, way down, because, and it's, largely dependent on load, but also largely dependent on the type of soil. There are types of soil that the soil engineer comes back to you and says, hey man, this soil can take almost zero like skin friction. You're digging in sand. You have dirt, and then you have 20 feet of like weird sand shale that can't take any value. You have to go below that to get structural, like safe soil.
Dude, so
So that
that
means
that was what
that means
just
you're
came to
sending your
mind. It was like
pile down.
I was just thinking like when you dig on the beach, like as a kid, and you're like digging in sand and you're like, oh my God, this is so cool. And you try to dig a tunnel, it's super
Mhm.
hard.
Yeah. hmm That's from
It all like,
the pressure of the weight from the soil above it. But yeah.
dude, that's wild. 100 feet deep and 3 feet in diameter or more.
hmm Yeah, and it's a huge cost impact. So these only really go on the fancy houses way up in the hills, that are just on bad soil in the first place. Um, but yeah, I mean, I've seen a soils report that gave us, like 60, maybe it was 40 to 60 feet of unusable soil. You have to go below that in order to get any kind of structural, capacity.
Okay, so and this is just to make the basically the first floor of the house be flat, right? This is not any part of the house building. So
Which
okay,
is, yeah, that's correct.
if you're digging, can you give a cost estimate of like, okay, let's say you have to dig 100 feet just because that's crazy. Um, like how much does that cost? Because I'm assuming you got to get a huge drill, and there's probably
Yeah.
not many people with equipment that can do that. So like how much does something like that cost?
So this is part of the I'm not experienced enough, where like engineering judgment kind of cost estimates come with time of doing these projects. Where I do all of the engineering and I hand it to my manager, and my manager then comes up with cost, how much he's going to charge a client, and then they kind of pass it off without consulting me or letting me know.
Got it.
So I
Got
don't
it.
exactly know the cost. I'm sure that it's Googleable, but it also depends on the county and the contractor. Um,
Right.
but I can tell you just from conversations when I've told clients, hey, it looks like we're going to need to do piles, around 20 to 30 foot deep, and they always give me a face like, no, we're not doing that. so so
We'll
from
build
from that
somewhere
reaction,
else.
from that reaction, I think it's very expensive.
Dude, that's wild.
Yeah.
Okay. So what's the difference between a foundation and a slab? Because you're 1,000% right. I was thinking that those are the same things.
Yeah.
So
Yes.
you have your pad footings, your linear footings. You got
Mm-hmm.
that's all taken care of. Your foundation's
Yep.
good. What the heck's a
Yep.
slab?
So the slab. So you need to be able to put your hardwood flooring is not going to sit on the dirt, right?
Mm-hmm.
You need a flat surface where you can start putting your walls down, and you can start laying out your plumbing down, and you can start working on like a flat area. And so that's what we call slab on grade. At least in the most typical form is slab on grade. Again, like every portion of what I talk about has multiple. They're all umbrella terms where
Right,
like
right, right.
we're picking a slab on grain, but there's also raised foundation. There's also mat foundations. There's also concrete slabs if you're on like bad soil. So like, but this is in the most typical form is slab on grade. You pour. It's usually 4 inches minimum of concrete over the entire site from starting at the perimeter, the outside edge of those continuous footings that you poured,
Mm-hmm.
and then it takes up the entire building space. And so that's 4 inches thick. You usually put number four bars at 16 inches on center, going each way to help that slab not experience cracking, because the
Mm-hmm.
steel kind of helps hold it together. Um, and so, yeah, so you lay that all out and then you let it cure. And now you have a perfectly flat, perfectly clean building pad to work on. And you know the locations of the foundations underneath. So you know where your walls are going. And you can kind of go from there. But that's what the slab on grade is.
Got it. Got it. Okay. Okay.
Yeah.
Dude, that's wild.
Mm-hmm.
That
It's
is
pretty cool
so,
stuff.
so wild.
It's pretty cool stuff.
So I don't know if I told you, but I recently got the chance to go to a Habitat for Humanity build
Mm-hmm.
and like see like they were building houses, they're building these duplexes in like for people to live in. And it was at the phase where like all the walls were up, all the but everything was bare wood. So like the walls were up, the floors were in, the roof was on, the windows in, they were like putting on siding and they were like like making some of like the shower installs be flush with the walls. Like that was our job, was to go in and like add pieces of wood to like make the showers flush. They can hang drywall.
Mm-hmm.
And I was blown away that, well, I just think I think buildings are crazy.
Yeah.
And like the fact that they get erected at all is nuts. Because
Yep.
like all of the teamwork and working together and like, okay, like you were saying, like structural needs to talk to mechanical, needs to talk to electrical, needs to talk to plumbing, and like all of those things need to crisscross and it needs to work in this way in a cost effective way. So I
It,
just think
it
buildings itself are crazy.
it's amazing that any of it gets done, and it's amazing that it's been getting done since the beginning of time, when we needed to build shelters in the first place.
Right. Right. Yeah, dude, it's wild. But
Yeah.
I was thinking as we were in there, I was like, man, there's a ton of people walking around on these floors. And like from what I could tell, all of the like all that the floor is, at least on like the second story. So like you go up the stairs and all I saw was like pieces of plywood.
Mm-hmm.
So like what the heck is a floor? And how is that okay to walk on? Cuz like I'm looking at this, I'm like, I definitely have like been able to break plywood before, and I'm
Yep.
like
Yep.
walking on this thing and it's no one's freaking out. And like intuitively, I know that it's fine, but also I know that plywood's super not strong. So like, how does that work?
Well, you, my friend, you are walking and enjoying the fruits of a structural engineer's labor. That's what you're doing. Because everything was specifically designed to support any kind of construction weight and any kind of weight um, being delivered to that plywood. And so let me kind of go into that. So the floor is made up of joists, which
Okay.
span wall to wall or wall to beam, depending on the situation, and are designed for a certain amount of weight. And so there are two types of weight. Well, there's a lot of types of weight. There are two typical types of weight. Your dead load and your live load.
Okay.
Dead load is anything that will permanently be sitting on that joist. We're talking weight of the plywood, weight of any of the architectural finish. Um, that's, I mean, that's basically it. There's small other like very niche things that could be on there, but
Like
that's
water in
really
the pipes or something.
we do account for piping or for like any kind of mechanical, if there's a big mechanical unit sitting on a specific area, we will
Uh-huh.
account for that. Um, but we just do worst case scenarios, which usually is full piping, which I think I typically, for pipes, I spread it out over the whole floor and I say it's all right, your piping with water full is it's gonna add around 4 pounds per square foot to the entire building. And I apply
Okay.
that everywhere. Even if
Okay.
pipes aren't there, we're just gonna spread it out over the whole thing and everything's gonna work kind of as an assembly
Okay.
put together.
And,
Um,
and so sorry, going back to you were saying that like joists go wall to wall. So like I'm
mhm,
imagining, okay, you have, your walls are up and you're adding a second floor. So okay, so
yes.
you're putting wood across from wall to wall or wall to post,
Mhm,
like you were saying.
mhm,
And then
yes.
what? You literally can just like stick a piece of plywood down and you're good.
Well, so you design that joist to be a certain size based on the load. So the load, so we have the dead load, and the live load is anything that can be moved on it. So that's
Mm-hmm.
people, that's furniture, that's plants, that's just stuff.
Mm-hmm.
And so we put a general code required load of 40 pounds per square foot if it's a second floor.
Okay.
Um, and I wish could use my camera because I have a diagram of what 40 pounds per square foot looks like. I can send it to you after if you want to post it up.
Okay.
Um,
Okay.
but it's basically, if you imagine like an elevator, it's a full elevator is like 40 pounds per square foot. And so we apply that load over the entire floor, right?
Okay.
And so then from there you can just design your joist. How much material of wood do we need to resist that load, and how far do we need to space these joists apart?
Got it.
So
And so
right
yeah, so what is that? Like what's a typical joist spacing for a second floor?
it it is very typically it's like 2x10s at 16 inches on center is what I normally it like in the very most typical house that will
Oh,
almost
okay.
always work.
Okay.
Or 2x12s if it's a little bit of a heavier floor. Two by 12s at 16 inches on center. In construction, we always do either 16 inches or 24.
Uh-huh.
Um, and that's so that they have, I mean, in cases you can do 12, but it's so that they can fit um, plumbing lines and mechanical lines and ducting through these spaces in between where you're walking and the ceiling below where you're walking, if that makes sense.
Where you're
There's ducts
walking.
running.
Yeah. 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 Yeah.
There's like
It does.
ducts and piping and there's stuff running. Your house is like a living, breathing thing,
Right.
right? And so
Right.
there's stuff running in every direction under your feet and you don't even know it. And so that's why we choose 16 inches on center so that we can run those lines of ducting through the floors.
Got it.
Um, and so then the plywood then has a span rating of like, oh, this plywood can span 24 inches or 48 inches without needing a support below, without breaking, based on
Mm.
some load. Um,
And so
but
because you have 16 inches, not 48,
yep,
you're fine.
you're fine. That plywood will not break. You'd have to really, really, really try to break it, especially when the joists are 60 inches on center.
Right. I mean, I was definitely jumping around up there, just not trying to break it, but just, you
Yeah,
gotta
yeah,
you gotta test
testing.
things out every now and again.
Yeah, exactly, exactly. But yeah, so those things are all designed for ahead of time to get the sizes right, to get the plywood right, so that you can walk around and continue building.
Okay. All right, that's fair enough. That actually makes a lot more sense than I thought it would. What about like like skyscrapers, like concrete floor skyscrapers that are
Yeah,
going up, 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 for hundreds of, maybe not hundreds, but like, a 40 or 50-story building that your every floor is in between. You have a bunch of concrete.
yeah. So that's a whole different ball game. I've only worked in the single family residence industry, but the
Okay.
company I work for, they do a bunch of apartment buildings. They did parts of SoFi Stadium, parts of the new Clippers Arena. They've done kind of things all over the map. Um, And from when I talk to my colleagues, it's a much different process, and I deal with different problems than they deal with. And it's um, we have funny like war stories to tell each other at the end of the day. Um, but I think the idea is relatively the same, where they so instead of designing joists, they design a concrete floor using any kind of um, at least nowadays, any kind of structural engineering software where you can draw out what your floor slab looks like,
Uh-huh.
and put different weights in different areas and different point loads coming down, and then run this structural analysis, and it's called finite element analysis.
Oh yeah.
Uh, yeah, FEM. What's the M stand for? Oh, finite element modeling, maybe.
Okay.
And it can tell you how your slab is gonna move, where the weight is all gonna go, based on based on meshing together this concrete and kind of um, doing a lot of matrix math to get like a value of how thick does your concrete need to be, how much rebar do you need to put it, where do you need to put it, and where is the weight going and how much weight is it.
And I guess for that, instead of having joists, like you were saying, you'd probably just have like columns or posts throughout the floor to hold up the section, right?
Correct. And if you don't, yes, and if you don't want columns or walls or anything, and you just want to span it perimeter to perimeter, you're gonna end up with a much thicker concrete slab. So like, um, it will typically be anywhere from like 10-inch thick concrete slab to like 14-inch thick concrete slab. Of course, they get smaller and bigger,
Uh-huh.
um, depending on how much money you really want to spend on it. But I think in the most typical form, they're like 10, 11, 12 inches thick.
And then maybe this is not correct, but my intuition, if you did want to have no columns and you just wanted to have a concrete span, that would all those loads would just need to be accounted for on the like in the foundation. So even if it's a 30-story building, you probably just need to have a way deeper, thicker,
Mhm.
bigger foundation to
Yep,
take all that weight.
exactly. At the end of the day, all we're trying to do is dissipate that weight into the earth
Right.
some way somehow. And so depending on the weight, just the deeper you need to go, basically.
Dude, that's wild.
Hmm.
That's
Yeah.
wild. Do when you're like driving around LA, do you just like look at buildings, you're like, whoa.
uh, just constantly. It's like a weird obsession, and it's even cooler when I know that I've done the project, right? I get to
Mm,
drive around these fancy neighborhoods and be like, oh, I did that one. Oh, I did one down the street. Let's go check it out real quick.
right,
Okay.
right.
Oh, I think we put in a bid on this one. Let's go check it out and see if I can see anything cool. Like it's a constant. Uh, I mean, I think at this point my fiance is over it, but it makes her late more often than not because I have friends. LA is a big place, but you drive through these little mini cities, and you're like, "Whoa, I need to go check this out. This is really cool."
Right, right.
Yeah.
Is there anything that you're excited about like in the future, like you were saying, we've been building buildings for since the beginning of time, right there, or building structures rather.
Mhm.
Is there anything that you're like, dude, I can't wait for this to come out? I think it's going to change the game when it comes to like building technology.
There's a lot of things, and I think it's mostly up to these private companies that build structural softwares, one, um,
Okay.
and like structural hardware too. So, like the first example, structural software, that's things like Revit, made by Autodesk, which let
Mm-hmm.
you model everything. So you have a perfect 3D analysis of exactly every structural component that needs to go into your house. You can walk through it, you can show it to the architect, you can detect any clashes between plumbing, electricity, structural, architectural, and get a totally fully comprehensive view of what your building is going to look like before you even put the first shovel into the ground.
Mm-hmm.
Um, and it gets better by the day,
Mm-hmm.
and modeling gets better by the day. So that's one. That's kind of but and Revit's just one of many companies that does this. That's just for example. And then the second is the actual hardware that we're using. We have reps come into our office all the time to try selling these new products, and they give us usually like an hour-long presentation of like, hey, look what we created. It's so helpful. Here's how you use it, and here's what this is all about. And so these are things like, oh, we designed this new link between two steel members that, like, if an earthquake happens, it guarantees the life safety of the people in your building. And then instead of like needing to replace the building after an earthquake, you could just replace this fuse. It's basically a fuse between links in a
Hmm.
building. So instead of tearing down a building and having to rebuild it because it's a ruin from an earthquake because it like deflected too much or whatever,
The
you
fuse
can just
just
replace
breaks.
these. Yeah, you can just replace these little. They're called yield links that Simpson Strong-Tie makes, and it's like, whoa! I mean, that's changing the game, right?
Right. Right.
Um, but it even gets down to like, oh, Simpson Strong-Tie just created this new screw, and this new screw has double the capacity that the old screws have. Um, it's faster to install, so it's cheaper for the laborers, and it's cheaper to make because they figure out some way to do it in the factory, and it's fully tested to be approved in LA. It's like, whoa, like the game is constantly being changed, and because it's a private company, they're all competing with each other and trying to best each other.
Right.
Um,
Right.
and we're the benefactors of that, where we get to sit in our office and people get to come to us and buy us lunch and try to like, oh, you should use this one, like put this one on your drawings. Oh, you
Right.
should spec this product because we're going to be cheaper and we're going to help you out more. So it's kind of like a fun little game where we get to sit and be the thumbs up or the thumbs down when they come in. Yeah.
What are and maybe this is a bit of a tangent, but like, what are your thoughts on like modular construction?
Uh, I I think it's a really good idea. There
And
actually is a house that is we're down the street that just did modular, and it's a single family home, which is pretty rare.
so
Uh,
what maybe can you like give a definition, like a rough definition of modular construction as you understand it? Because I think I know, but I don't
yeah.
really know.
So modular construction is kind of if you can imagine, it's like stacking shipping containers
Mm-hmm.
um, on a site and just matching them next to each other or on top of each other and opening spaces so you can put stairs in and connect all of them. But
Mm-hmm.
instead of shipping containers, you're like making actual rooms.
Okay.
And so you're shipping rooms one by one, basically. And
Okay.
the idea is that we're in California, so labor costs a lot more. If you can do the labor part in Idaho and then just ship these modules of rooms to California on a truck, that's much cheaper than having someone custom build a home in California
Sure.
or in Los Angeles specifically.
Sure.
So then you can offload these pre-built rooms onto your site off of a truck, set them into the foundation, lock them all into place, put the next one in, put the next one in on top of that, connect the two, and then boom, you have a house, a modular
It's like building
home.
Legos, like adult
It's
Legos.
exactly, it's like building Legos, and I think it makes a lot of sense for things like hotels where you have the same room
Mm.
over
Mm-hmm.
and over and over and over again. You don't really have a lot of change in the structural engineering or like the structural requirements.
Right.
It becomes a lot harder when it's like a home that things change from not even room to room, but like square foot to square foot.
Right. Right.
Um,
Right.
So it's a lot more challenging to do it that way, but it is doable. I've seen it. It is doable.
Interesting. What are your thoughts writ large on that? Like, think it will be bigger in the future, the same in the future, or smaller in the future?
I think it's going to be roughly the same, maybe bigger in the hotel space,
Okay.
or apartment space. Um, just I also just think it's newer, and so the idea is, oh my God, this is going to be so much easier to design and so much easier to implement. But all of that comes at the expense of inexperience. It ends up taking the same amount of time because mistakes happen. You're not really used to the construction form. You can't just, you have to have a very specific contractor that knows how to do it well.
Right.
Yeah.
Yeah, that makes sense. That makes
Yeah.
sense. Huh. Dude, this has been so fun. I thank you so much. I feel like I could talk to you for hours. And
Yeah, I hope some of the stuff didn't get too boring in the middle there. It can be dry, but once you get to see the finished product, the actual architectural finishes and like what the building looks like, it can be breathtaking.
yeah. Are there like, do you have a favorite building in the world?
Ooh, a favorite building in the world. Oh man, there's a lot of them. Well, I'll say my favorite building that the company I work for has done, is one in LA. And I can send you a picture of that to post up there as well. It's on a street called Orem Road, and it's just like I said, breathtaking. Um, when they have like a drone footage of it going through the site, and you don't understand how these things are physically possible, how the engineering and how the engineering and architecture did such a good job. It's like, I mean, it's crazy. So that's in LA. Um, in the world, I think that the Burj Khalifa, it's so stereotypical for a structural engineer to say that, but I mean, the sheer size of it. I don't know if you know what the Burj Khalifa is, but it's the tallest building in the world. Um,
Okay.
and like the size of it is just astounding. Like it's, I mean, I've only seen pictures. I want to go there. It's in Dubai. I want to go there eventually. Um,
Okay.
but I mean, it's insane. It's an insane building.
Dang.
Yeah, yeah, man. It's so funny that when people say like, oh, what do you do for work? It's like, oh, I'm a structural engineer. It's like, oh, cool. So what do you want to get for lunch? It's like, oh, there is so much to go. There, I can go deep. I can I can tell you exactly how many nails you need to put in a single piece of plywood, in order for it to withstand an earthquake of a certain size. But yeah, no, let's go get a sandwich for lunch. Which I guess is
Oh
true of
my
any
God.
industry or any job, but yeah.
Right. Oh, dude, I love just hearing you talk about buildings. It makes me happy listening to you being happy talk about buildings.
I love it. I love it. I love talking about them. So invite me here anytime.
There's gonna need to be a part 2 with our cameras working,
I
so you
love
can
it.
explain with your hands how live loads and dead loads work. Um,
Amen.
where can people find out more? Like, find you online if they want to reach out, ask questions, etc. Where's a good place for people to find you?
So I'm on LinkedIn, Gil Hetsroni. If you just search me up, I work for a company called Labib Funk and Associates. So you can kind of search on our website and contact me there. But those are kind of the best places to go. And yeah, feel free to reach out with any questions. I'd be happy to answer them or kind of guide you if you want. If this kind of stuff interests you, then come talk.
Yeah, if you have any engineering questions, Gil is the best resource. I use him all the time, probably a little too much. So apologies, my friend. Gil,
Happy to help always.
dude, thank you for being here. Thank you for doing this. I appreciate you. I'm looking forward to the next conversation.
Yeah, man. Thanks for having me on. Sorry about the no cameras, but we made do.
Hey, it happens. It happens.
Yeah.
All right. Thanks, everybody.
Thanks,
Bye.
guys.